The massive bursts of heat we observe in chemical reactions do not appear spontaneously. They are strictly governed by microscopic rules of accounting. To understand exactly where this thermal energy originates, we have to look past the macroscopic reaction and examine the architecture of the chemical bond itself. Every chemical bond functions as a tiny storage vault. The final thermal outcome of any reaction is entirely dictated by the energy banked within these individual connections. This diagram illustrates the precise chemical definition of bond energy. For a hydrogen molecule, it takes exactly 436 kilojoules of energy input to shatter that connection. But this value comes with strict limitations. That 436 kilojoules applies exclusively to breaking exactly 1 mole of that specific covalent bond. Furthermore, the molecules must be entirely in the gaseous state. This isolates the bond energy from other variables, ensuring we are not accidentally measuring the energy required to overcome intermolecular forces in a liquid or a solid. Because of these strict parameters, we measure this thermodynamic value using a standard unit, kilojoules per mole. By mastering the mechanics of breaking and forming these specific connections, we can mathematically predict whether any reaction will absorb heat from its environment or release it. Ultimately, chemical reactions operate on a closed thermodynamic ledger. Energy is never created or destroyed. It is only invested to dismantle old bonds and returned when new ones form. To calculate these energy exchanges, we first have to recognize the physical reality of atoms. They are locked together by underlying electrostatic forces. A covalent bond is a precise state of tension. The positively charged nuclei of two atoms are mutually attracted to the negatively charged electrons they share between them. Forcing these attracted particles apart requires you to physically overcome that electrostatic grip with an external input of energy. Because this specific step always demands a thermal input, breaking bonds is strictly defined as an endothermic process. Now reverse the scenario. When two isolated, highly reactive atoms approach one another, they quickly snap together to form a bond. By locking their shared electrons into place, these atoms achieve a far more stable energy state than they maintained while separated. Dropping to that stable state forces the atoms to shed their excess energy outward into the environment. This release of stabilizing energy is strictly an exothermic process. We can distill this down to a foundational axiom. Bond breaking guarantees an energy penalty, while bond formation guarantees an energy payoff. If every bond requires an energy penalty to break, why do some snap easily under low heat, while others demand massive thermal investments? Bond energy is not a flat rate. It is dictated almost entirely by physical geometry. Looking at this comparison chart, we can isolate the two primary variables of bond strength, atomic size and bond length. Notice the inverse relationship. Shorter bond lengths naturally pull the positively charged nuclei closer together. This proximity increases orbital overlap, the literal physical space where the shared electrons exist. Greater orbital overlap creates a tighter lock between the atoms, which directly increases the energy input required to break them apart. The most effective multiplier of this overlap is bond order, whether the atoms share a single, double, or triple bond. A single bond between two relatively large chlorine atoms requires an input of 242 kilojoules per mole to break. Compare that to a single bond between two much smaller hydrogen atoms. Because the nuclei sit closer together, the required energy jumps up to 436 kilojoules per mole. But when we examine a nitrogen-nitrogen triple bond, the data spikes dramatically, requiring an immense 945 kilojoules per mole. Sharing 3 electron pairs pulls the atoms into extremely close proximity. That short length and massive orbital overlap create an exponentially stronger electrostatic lock. The strength of a chemical bond is effectively just a function of proximity and the resulting density of shared electrons. Isolated single bonds are useful for learning the rules, but real chemical reactions are chaotic environments where trillions of bonds are broken and formed simultaneously. To track the total macroscopic heat absorbed or released by this entire system, chemists measure enthalpy change, represented by the symbol delta H. This equation functions perfectly as a thermodynamic ledger. It calculates total input versus total output. On the left side, we tally the sum total of all endothermic energy required to break the initial reactant bonds. On the right side, we track the sum total of all exothermic energy released by forming the new product bonds. We can test this ledger using a standard case study, reacting hydrogen gas and chlorine gas to form hydrogen chloride. We establish the reactant side of the equation first. Dismantling 1 mole of hydrogen-hydrogen bonds exacts a strict energy cost of 436 kilojoules. Dismantling 1 mole of chlorine-chlorine bonds adds another required input of 242 kilojoules. The reactant side of the ledger always represents a gross investment of energy that must be paid before any new structures can be assembled. We sum the gross investment required to break the reactants apart. 436 plus 242 gives us a total input of 678 kilojoules per mole. With the initial molecules dismantled, we shift focus to the right side of the ledger to log the products formed. The chemical equation dictates that this specific reaction produces exactly 2 moles of hydrogen chloride bonds. The exothermic release for forming a single mole of HCl bonds is 431 kilojoules. Because we form 2 moles, we multiply that release by 2, giving us a total gross energy return of 862 kilojoules. The data reveals an immediate tension. The system released significantly more energy building the new bonds than it consumed destroying the old ones. Executing the final enthalpy equation confirms this. We subtract the 862 kilojoules of formed energy from our 678 kilojoules of broken energy. The calculation resolves to a net value of negative 184 kilojoules per mole. This establishes a universal thermodynamic rule. Whenever delta H produces a negative value, it guarantees the overall reaction is exothermic. That negative sign represents a physical reality. The reaction system has permanently lost that heat, radiating it away into the surrounding environment. For exam applications, this is the primary mechanic to remember. Net enthalpy is simply the difference between the endothermic breaking of initial bonds and the exothermic formation of new ones. And the math only holds up if you respect strict parameters. Calculations must assume the gaseous state and rely on exact molar quantities. By treating chemical reactions as a rigorous energy ledger, you strip away the mystery of thermodynamics. You learn to track the heat, predicting the outcome one calculated bond at a time.